One theory, two backgrounds, four forces, and 104 years.
This is the theory of everything. The four forces of nature: electromagnetism, strong nuclear, weak nuclear, and gravity. For over a century, the main goal of physics has been to unite these four forces into a single fundamental framework, creating a theory that describes, well, everything. Electromagnetism and the two nuclear forces have already been united by the grand unified theory. Joining gravity to this would give us a theory of everything. But gravity isn't exactly cooperating with the unification process. You see, the first three forces all follow the laws of quantum mechanics, so their unification was somewhat simple. However, gravity plays by a different set of rules. General relativity.
General relativity defines gravity as an effect felt due to the curvature of the space-time background.
Quantum mechanics, on the other hand, doesn't really have a flexible space-time background. And when you try to add one in, it creates infinities and non-predictable results. If general relativity defines gravity as the curving of the space-time background, and quantum mechanics can't have a curving space-time background, how can there be a theory of quantum gravity? If there isn't a quantum theory of gravity, then a theory of everything can't be possible. But the possibility of impossibility has never stopped scientists from trying. The most popular candidate for the theory of everything is string theory. String theory is the idea that the supposed point particles of the standard model are actually one-dimensional vibrating strings. These strings, in different directional shifts and vibrational frequencies, can create different particles. One of these particles is the theoretical graviton, which would be the force-carrying particle of quantum gravity. String theory has simplicity, symmetry, and beauty. What's the catch?
Richard Feynman said, "It doesn't matter how beautiful your theory is, if it doesn't agree with the experiment, it's wrong."
Although a beautiful theory, when string theory has been put to the experimental test, it's failed every single time. However, there is another major candidate to potentially quantize gravity. Loop quantum gravity is an attempt to formulate a theory of quantum gravity using Einstein's geometric interpretation of spacetime. This spacetime background is comprised of loops, which on a quantum level looks separate and fluctuating, but when put to the levels of general relativity, appear just as Einstein predicted. Loop quantum gravity isn't as beautiful as string theory because it doesn't try to connect everything. But because of this, it's more widely accepted. Even with a more narrow focus, loop quantum gravity still lacks any experimental evidence. Where can we go from here? Science has seemed to hit a block when trying to find a theory of everything. We've searched for over 100 years and yet an answer still seems impossible. We need to continue pushing forward to find the answer to the impractical, impossible, everything.